Okay, so today we are talking about systems of equations and how to graph them. So there are three types of solution. The first type is when we have one solution. If we have one solution, that means we have two lines that intersect at one point. No solution, this is when we have parallel lines, so two lines that never intersect. Infinitely many solutions, these are coinciding. That means that they are graphed one on top of the other, basically graphed on the same exact line. We call those coinciding, and that is infinitely many solutions because they are touching at every single point. Okay, so for our first example, what is the solution of the system? I have negative 3x plus 2y equals 8, and x plus 2y equals negative 8. So I am going to start by putting my equations in slope-intercept form. So remember, slope-intercept form is y equals mx plus b. So we're trying to isolate the y. So for our first equation, negative 3x plus 2y is equal to 8. We will start by moving the x to the left side. To move a variable, we have to either add or subtract it, and it depends on what the sign is, if it's a negative or a positive. So in this case, it's a negative 3x, so we are going to add 3x. And we are going to do that to both sides. So we end up with 2y equals, and remember we're trying to make it look like this. We want the y equals mx plus b. So the x term needs to come first, and then our constant, the number, whatever, needs to come second. So that means we're going to put 3x first, and then plus 8. And then the last step to isolate y is to get rid of the 2. So this is 2 times y. In order to undo that multiplication, I need to do the opposite of multiplying by 2, which is to divide by 2. So I end up with y equals 3 over 2x plus 4. And we want to leave this as a fraction because we're going to be graphing it. We want a rise over a run. So the first point we graph is the y-intercept, so I'm going to take 4 and plot that on the y-axis. So go up to 4, plot a point. Next, I'm going to use my slope. My slope is 3 over 2. So this is my rise over my run. I'm going to start at my y-intercept, and I'm going to go up 3 over 2. Up 3 over 2. And plot my points. Okay, and then we draw our line in.
How many questions? 5 more questions.
Brian, you're showing up on the video. And I'm going to leave it in there just to teach you a lesson.
You have to say something.
Okay, and now we need to figure out our second line, putting that in slope-intercept form. That's way too big. So we have x plus 2y equals negative 8. We're going to follow the same steps that we followed for the first one. So I start by moving the x. This time it's a positive x, so I'm going to subtract it. So I end up with 2y equals negative x minus 8. Okay, and then I divide by 2. I'm running out of room, so I'm just going to write it, move that right over here. So I end up with y equals negative x over 2. Remember, if there isn't a number in front of the x, that means it's a 1. So this is actually a negative 1x. So negative 1 over 2x minus 4. So I start by graphing my y-intercept. So the y-intercept for this one is a negative 4. Go down to negative 4 on the y-axis, plot a point. Ooh. Okay, and then my slope is negative 1 over 2, so that means I'm going down 1 over 2, down 1 over 2. Okay, it's gonna kind of run into my work here. That's okay. All right, and then I draw my line in. No. No. Okay, I'm gonna pause this and do it. Okay, and there's my line. So the original question was asking for the solution of the system. So solution of the system is going to be wherever my two lines meet. And actually my lines are a little off, so I'm going to fix those. Remember to use a straight edge if you're writing these on paper, otherwise it might come out to be the wrong answer. Okay, that's better. So, now that I fixed my lines to make them a little bit straighter, make sure they're going through all my points, I'm looking for where they intersect. That is going to be the solution of my system. So it looks like they intersect right about here. That point is at -4, -2. So that is my answer. Okay, so next we're going to talk about the difference between consistent and inconsistent, and independent and dependent. So a line or a system of equations, the lines are consistent if they cross. So if they are touching at one point, or if they are touching at infinitely many points. So for example, okay, if I have one line going this way, and a second line going this way, they intersect at one point, this is consistent. Consistent means that they intersect at least one point. So another example of consistent is if they intersect at all points, infinitely many points, if they coincide. So if I have my red line, and then my blue line ends up being graphed right on top of my red line, and that's a little terrible, let's try that again. Okay, these lines coincide, one's graphed right on top of the other. This is also consistent because they are touching at least one point. And for this one, it's actually infinitely many points. Those are consistent. Inconsistent would be if we have parallel lines. So, okay, so if I have one line going this way, a second line that's going up at the same slope, the same rate, they never touch, these are inconsistent. They never touch, not even at one point. We call that inconsistent. Okay, and then the difference between independent versus dependent. So an independent line or independent set, that's when we have lines that are crossing at only one point. So if I have my red line, my blue line, they cross at one point and one point only, that is independent. If I have my red line and my blue line where they coincide, so one is graphed right on top of the other, that is dependent. So can we determine the number of solutions and classify the equation without graphing? So just given the equations, can we do this? Yes, we can, and I will go through how. So for no solution, we say it's inconsistent. That's if I have an equation, or two equations really, that have the same slope but different y-intercepts. So for example, if I have y is equal to 3x plus 1, and then my second equation, y is equal to 3x minus 6. If our equations have the same slopes and different y-intercepts, we know just from that information that these are parallel lines. And so I would already say that's no solution and it is inconsistent. For one solution, that's when we have two lines that have different slopes and different y-intercepts. So if I have y is equal to 6x minus 4, and my second line, y is equal to negative 1/3 x plus 2. This is an example of one solution. We have different slopes, different y-intercepts. From that information, we know that it is one solution, which means it's consistent, and it is independent. And then finally, an example of infinitely many solutions. Given the equations, if our equations have the same exact slope, so let's say y equals 2x plus 4. If they have the same slope and the same y-intercept, and these don't necessarily have to be in slope-intercept form. If I had 2y equals 4x plus 8. The first equation's in slope-intercept form and the second one is not. We remember we need to put them in slope-intercept form before we can actually compare the slopes. So I would take this second equation and I would divide each of my terms by 2. And when I did that, I'd end up with y equals 2x plus 4. So that's when I have infinitely many solutions, when it's really the same exact equation. And when I graph them, there's just going to be one graphed right on top of the other. So if we have something that looks like this, from our equations we can tell that it is consistent and it is dependent with infinitely many solutions. Okay, so for example, I have y equals negative x plus 3 and y equals 3 halves x minus 2. So for my first problem, my slope is negative 1. That's the number that's in front of x. If there's not a number there, that means it's actually a 1. Okay, so my slope is negative 1, my y-intercept is 3. For my second one, my slope is 3 halves, and my y-intercept is negative 2. So just from that information, they have different slopes and different y-intercepts. That means I know that it is one solution, it is consistent, and I also know that it is independent. For my second example, I have to actually rearrange these equations first. So rearranging my first equation, I start with 2x minus 2y equals 4. We're going to do similar to what we did in the first problem. Move the x over, divide by the number in front of y. So I will start by subtracting 2x. So I get negative 2y equals, remember the x term needs to come first and the constant comes second, and then divide by negative 2. So the equation for my first line is y equals x minus 2. The second line, we have y minus x is equal to 6. For this one, much easier here. All we have to do is move the x. There's not a number in front of the y, so once I add my x to both sides, I end up with y equals x plus 6. So now I have two equations that I can compare. So for my blue equation, it looks like my slope is 1 and my y-intercept is 6. For my red equation, my slope is also 1. Right? If there's not a number in front of the x, it's just a 1. And my y-intercept is negative 2. Okay, so it looks like I have the same slope and different y-intercepts. So if they're the same slope and different y-intercepts, that means that I'm dealing with parallel lines. So there is no solution for parallel lines. They never touch. And they are inconsistent. Inconsistent just means they do not meet at any points. Okay, that's the end.